Okay, so assignment 3 has been, the deadline of assignment 3 has been deferred to Wednesday, 11:59 p.m., the end of the day. So hopefully this is going to be useful for those of you who suddenly need to move. Okay, and assignment 4, originally the deadline would be on Monday next week. But to give you more time, we will just defer it accordingly, right? This is also on Wednesday, the end of the day. Okay, so that's all for the announcement for today. So this is now week 5, which is we are going to this week we are going to learn even more equations. You by the end of this week, probably by the end of this lecture, you will get a lot more equations, and if you like those, that should be very good for you, because you should see it as a fact that you have more tools in your toolbox for doing thermodynamics. Okay, so let's move towards there. Okay, so last lecture, what did we learn? So last lecture, the most important, now we have done a lot of things to be to have continuity. I will quote some results. Okay, so we learned Joule's expansion. So this is a result that we need today. So Joule's expansion. We learned how to analyze the process. We learned how to calculate the entropy change. So we find that the entropy change for this particular case, we analyze. That is to say, we assume the volume change is exactly a factor of 2, right? The initial volume was V, the final volume is 2V, and then we can get a very concrete prediction. We calculated the entropy change, and the entropy change has this factor here. So we have the entropy change, in this case, the entropy change of the gas, really. So for the ideal gas is exactly N Kb log 2. Okay, so this log 2 is a factor which we want to try to get today. Okay, and then we also talk about isothermal expansion, and then we discuss how to calculate this. So I will not repeat. You're encouraged to watch the video if you are lost at this moment. Okay, another thing is this. This is from last lecture, very last slide from last lecture, and this is this guy here. This is about attaching meaning to this mysterious function of state, which we call the entropy. So what exactly is this guy? This entropy, we try to discuss a little bit, and these are from last time. So this is related to information. Okay, so how do we get the information? How do we add the amount of information? And how do we formulate this entropy in a consistent way for us to do all this, right? And I use the dyes as the example. Right? This is also consistent with probability theory. How do you add probability? Okay, so this is the heart of statistical mechanics. And then we are going to build on top of this and try to get this result. Okay, so this is the first part of the course of today's lecture. Okay, so continuing this. So this is the Boltzmann's idea. We want to use log. So the idea is we need to we could have used omega, which is the number of possible arrangement, but we do the log because we want to add information. We need to add probability. Okay, so now what is this omega? This omega is the number of microstate, and this is really an idea due to Boltzmann, and people didn't believe him, and it turns out to be really the fundamental postulate of of statistical mechanics. Okay, so Boltzmann's idea, what did he want? So Boltzmann. Okay, he said that this number of microstates, I will just write again, the number of microstates is something we care about. So the number of microstates, and if you know this number of microstates, you will be able to make progress and link it to the entropy. Okay, so this is this number of microstate is what we call the omega. This number is this is this omega that goes into here. Okay, this omega. Okay, so let me try to be a little bit more concrete. You will see it very you get a very concrete definition when we get to statistical mechanics, but for the purpose of explaining the Joule expansion, I would say a little bit more. So let's, in this case, let's look at a system of gas, and now switch to the statistical mind. And in this case, what do you see? You see this not just as a volume, not just as a system with a volume, a system with some pressure at some temperature T. So you see this as a bunch of particles, right? Because now we try to look at the information content in this system, right? We need to go and examine all these particles. Okay, and what can we do? You can imagine asking the following questions. I want to know all the positions and the momentum. And if you are in three-dimensional space, you can have you really have for each particle you have x, y, z. You want to know the position of a given particle, and you want to know the component of the momentum. This is a vector. Momentum is a vector. Okay, so you have all these positions and momenta for all particles. Okay, right, so I have this system. I ask you, what is the possibility? Okay, you will tell me, okay, the particle can be at this position, the particle can have this momentum, and this is for n equals 1 particle. I label it as n equals 1, and then you have n of them. You give me all of this. Remember, when we still have face-to-face lecture, I use one example, and that is the midterm score, right? And I want something like this. I want a lot of detail, and this is only one microstate. And therefore, you can imagine the number of microstates is a big list. This is a huge list. Okay, so this is only one microstate. If I want all possibility, and this is a big number, a big a list, right? So it's a big amount of information. Okay, and macroscopically, what do you have? If you look at this system macroscopically, what you want is to ask a different question. You ask, what is the pressure of the system? What is the volume of the system? What is the temperature of the system? So this is this describe the macroscopic. This is an macroscopic property. Okay, so this macroscopic property, this can correspond to a huge number of microstates. Okay, that is to say, you can have a different microstates, which will give you the same PVT. Okay, so this can correspond to. So I would say, how should I write it? I would say, okay, more than one microstate can give this, can give the same macrostate. Okay, and therefore this in statistical mechanics term, you will see something called the most probable microstates. There is the microstates that will give you what you observe. Okay, so this there we will need to draw some distribution, and this will be we will spend weeks on this when we get to that point. Okay, so now here is the key. We cannot prove this. That's why it's called a postulate. So this is Boltzmann's idea, key idea, something that is associated with his name, right? So that is he claimed that this S, entropy S, not the change, there's no delta. Entropy S is related to this amount of information, log of omega, directly. Okay, and then if you fix a scale and if you choose the right unit, there will be a constant, proportionality constant that link these two. This is the log, or this is the amount of information, and this is what we call the entropy. And this constant is called the Boltzmann constant. Okay, and this is not too surprising, not too crazy, right? Why? Because look here, if you have a large number of microstates, you will have a large omega, then you have a large log, and you have a large entropy. And this is consistent with what we wrote here, right? So entropy is the freedom to explore. If you have a lot of microstates for you to explore, then S is large. Okay, so this is related to the large freedom to explore. So this is not too crazy. And second, you can add entropy. Right now, we know we want to be able to add information. This is what we learned from probability theory. Here, when we use the example of the dice, this is what we know. Okay, if you have a probability that you want to add, you add the log. But still, if you think in terms of thermodynamic quantity here, what is this entropy? This entropy is an extensive variable. We better formulate this in a way that allows us to add entropy. So if I have entropy of the system that I can subdivide it into two systems, subsystems, I know the entropy has to sum. So I will have S1 plus S2 equals total S, and that must be allowed. And that is a good news. The good news is now if you write it like this, you can add log. If you can add log, you can add entropy. So this is fine. Okay, so here this formulation is okay. It makes sense. Makes sense because we can add log omega, and therefore we can also add S. So S is an extensive variable. So this is because and this is extensive. Okay, another reason this is proportional to each other because if you have a large omega, then you have large log, and therefore large S. And this is consistent with the expectation that you will have large freedom to explore. Okay, and now I'm ready to discuss the Joule expansion to show you why you get this log 2, this factor of log 2. Okay. Now free expansion, we are going to analyze it. A free expansion, what do we have? The volume increased by a factor of 2, right? We choose to analyze exactly this problem. If you don't want 2, you can use 3, whatever, then you have different factor. But this is just a straightforward argument. Okay, and what else? we know it's an experimental fact that the temperature is fixed, right? After the expansion, the temperature doesn't change. And then we also know that the internal energy cannot change. So these are all standard result. Internal energy can't change. Now you have to think a little bit about this. If the internal energy and this is related to the ideal gas result, right? So it's easier to analyze it this way, and then think in terms of ideal gas. So temperature is fixed. Internal energy cannot change. And if you look at this body of thermodynamic system, this ideal gas, what gives you this internal energy? Now you think a little bit more microscopically. Okay, internal energy in the ideal gas, because by definition, the ideal gas, a particle in the ideal gas does not know the existence of other particles, right? That is the meaning of the ideal gas. Another way to say that is the interaction is very weak or zero, and therefore there should not see a potential. Okay, so there's no potential energy, which is due to the existence of other particle, right? This is how the particles interact with another particle. There will be some potential energy. So therefore, this U is exclusively kinetic. Okay, and the kinetic energy cannot change in this case, right? U cannot change, kinetic energy cannot change, and therefore, you know how to relate the kinetic energy to the momentum, and therefore the momenta remains the same. So the available, the momenta that you can explore, that they are available, that can be explored by all these particles remains the same. Okay, and therefore the thing that change will be the volume, which means the positions they are available for you to explore will become twice as much. Okay, so therefore the number, so combining this fact, the number of microstates, combining these two, so the number of microstates that can be explored by your gas particles becomes 2 to the n, 2 to the power of n more, right? So this is related to this kind of argument, right? Why do you have this n here, right? So for one particle can the number of positions available to explore by one particle becomes a factor of 2 more, and now you have n particles, so this is 2 to the power of n, right? So this is a number of microstates is increased by 2 to the n. This is because you have m particles, so this is n particles. Ugly. Okay, I write here. Because of n particles, and the 2 is because of this, right? So this is due to the fact that you can explore more positions. And how many more? So you have exactly twice as much. Okay, and now you can calculate the change of entropy. The change of entropy is, I'm going to use this formula. So the change of entropy is the final entropy minus the initial entropy. The initial entropy is some kb log omega. I don't know what omega is. Fine, but I know what I know is the final entropy has the omega amplified by a factor of 2n, 2 to the n. Okay, so before the expansion, I have this. I don't know the absolute value. I really don't know, because I don't know how to write this down. But for my argument for this justification, what I know is after the expansion, the number of position that can be explored will be increased by this factor. So this modify this omega here. Okay, and I take the difference, I will get exactly this result, nkb log omega. Okay, which is what I want to justify for you. Okay, so this is this nkb log 2. nkb log 2. Right, if you really take this out, you will see nkb log 2. Okay, so that is the end for this entropy business. Okay, I still have a little bit to talk about before we can close this chapter. Then we talk about analytical thermodynamics. So what else I need to do? Now this is really the same mathematics. So I want to I encourage you to look at the note for the full derivation. Okay, so I will just outline what is this problem. The same mathematics, because we are just following the calculation for evaluating Joule's expansion, the free expansion. Okay, but the problem is a little bit more complicated because now we are doing this. We are doing it this way. Okay, we are doing it. We have a partition. With a partition. Like this, and then we thermally isolate this to the outside world. Okay, so and we put some ideal gas here. This would be like the free expansion. Okay, but in addition to this, we add another. We prepare the experiment such that we have another ideal gas on the other side of the partition. And the other complication, which is again a very standard formulation in thermodynamics, is we set this to be this volume to be F times V, and this volume is 1 minus F times V. So when I write it this way, you know this F takes the meaning of fraction, right? So this can be a half of the volume, then this will be a half. So they sum to 1. Okay, and then a little bit more terminology, I will have N, which is the total number of particles, right? Not just on the left or on the right, is the total number of particles. Okay, and I prepared the experiment. I prepared the experiment such that so the experiment is prepared, is initialized in a way that initialize the experiment, or I prepare the experiment such that T and pressure on both sides are the same. Okay, so that's it. This is standard setup, and you are asked to find the change of entropy. What is the initial state? This is what you see here is the initial state, and what is the final state? The final state is when this partition is removed. Okay, so find the change of entropy after removing the partition. Okay, now this has a spatial name. This one is called the entropy of mixing, because you are really mixing the two different gases. For example, you can have helium, you can have nitrogen, and this is mixing the two different types of particle. Okay, so this is called the entropy of mixing. And why is this important here? First, I already show you this. Now, you are invited to do this. So this is the exercise. Try it first, because everything is defined for you here. And you want to find this result. You want to find the change of entropy versus the fraction f. Okay, everything is defined for you already. And if you the reason I don't want to do it is because the mathematics is identical to the Joule expansion. You just have two systems to worry about. And second, I think you can do it. So you should be able to do it in about 10 minutes. And you will get this result. I plot it for you, but you should verify. And you should then look at some spatial cases. So the spatial cases are here. Okay, you can think about this. Why you get 0, right? The change of entropy is 0 for these particular cases. I hope the reason is obvious. Okay, and otherwise your delta S is positive. Okay, that is to say this mixing here, this process is not reversible, but it's actually deeper, right? What is deep about this is we have to look at whether the system is distinguishable, just like the die, the question of the two dies, right? Here, for us to be able to do this, we have to assume that we can distinguish between the two dies, right? Otherwise, we will have a different issue, right? So here we should emphasize that we must be able to distinguish between them. For example, I can color it with red, the other one is yellow. And likewise here, it's important to think about this. So this is a precursor for you. So these two cases invites you to think about the distinguishability of this problem, which will be an important concept when we talk about statistical mechanics. When you have all these huge particles, whether they are distinguishable or indistinguishable turns out to make a huge difference. Okay, so here, when they are distinguishable, what happens? And when they are not distinguishable, what happens? So here, we implicitly assume them to be not distinguishable for this, to calculate this result. Okay, and you can think about what happens when they are distinguishable. Okay, so here I would write it here. I will actually write this line here. Say I'm not the same. So for example, I will have helium, I will have nitrogen, and when I remove them, mix. Okay, if they are the same, I have nitrogen, I have nitrogen on both sides. When I remove, technically I shouldn't see a difference. Okay, so this is some thought exercise for you. Okay, so I will put this equal sign here, right? Because here it can really be 0. So delta S is 0 at f equals 0, f equals 1. Otherwise, it's always positive. Okay, finally, I want to look at this problem. This is a little bit is interesting, right? This is the entropy of solid. Now, if we understand entropy as the freedom to explore, so what will happen? So I will say we will take a piece of solid, if you warm the solid, do you expect the entropy to go up or down? Okay, if I take a solid, if you use the viewpoint that entropy can be loosely thought of as the freedom to explore, so I can take a piece of solid and warm it. Do you expect the entropy to go up or down? Any idea? Okay, thank you. So entropy should increase, right? So entropy should increase. So this is a very reasonable reasoning. I take a piece of solid, I warm it, suddenly all these atoms have can vibrate more, and they have more freedom to explore a large configuration space. So I inject more heat, and then these atoms can vibrate more vigorously. So I would expect the entropy to increase. So this session is here to really convince you that although we say entropy is very abstract, but we should be able to use a few lines of reasoning to come up with a way to do experiment. Okay, this relates to a question asked last time. Okay, so there is one answer is given here, the other answer will be given later today. Okay, so how do we do this? What can we measure? So my claim is this: we can measure to prove this statement. Okay, to verify this picture, we can measure the heat capacity. Which is something we know how to do, very well. Okay, so now this is also in your assignment 4, so I don't want to say too much. For the purpose of here, I will also use this chance to talk a little bit about solid state physics, which is a course I used to teach. Okay, so now here, this is my claim. The heat capacity, if you look at this, this is really the heat capacity as a function of temperature. So the heat capacity, my claim is this: the heat capacity, let's say a heat capacity for solid, we really don't need to worry about whether it's constant V or constant P. So I will just choose one. Okay, the heat capacity can be written like this. Okay, so this is the heat capacity at low temperature. And at high temperature, heat capacity is a constant. Okay, so this is high temperature. Okay, this is the result from solid state physics. What do I mean by high and low? So this, you have to choose an energy scale to compare with. Right, so here, this energy scale, low temperature means that when the temperature is much lower than a temperature scale, which we call the Debye temperature. And this is much higher than the Debye temperature. Okay, so this is Debye temperature. For a typical solid, this is of the order of a few hundred Kelvin. Okay, so you can see somewhere here, if you choose 150, a few hundred Kelvin, to see this behavior, you have to go to very low temperature. And to see the saturation, you have to go to high temperature. Okay, now I say usually, if you look at diamond, for example, diamond will have a high Debye temperature, and you have to go to very high temperature to see the saturation. So this is something Einstein discovered, actually, that diamond is a very unusual solid. Okay, so this is a solid state knowledge, and you are asked to show in the assignment that this implies the entropy. I will have two lines, right? I can derive the relationship between the entropy and the heat capacity using thermodynamics. Okay, the entropy in this case will be will go as T cube at low temperature, and then it will go as log T, very weak function, but still increasing at high temperature. Okay, and therefore, now I want to complete the logic here. First, thermodynamics, then I will supplement some solid state physics here for you. Okay, thermodynamics. the logic is this. I claim this result. The entropy should increase when I warm it, which means entropy should goes up when I increase the temperature. And how do I know? I know because I know how I know the thermodynamics. I know my first law. I know how to do. I know how to analyze partial derivatives. I will be able to write down some relationship which you are required to do in your assignment form, and you can show that these are consistent statements. Okay, so with my thermodynamic reasoning, then I will ask maybe a summer student to go and measure a piece of gold, a piece of copper. You will see the heat capacity will go up like that. So this complete the thermodynamic argument. Okay, so that is nice. I know how to do this. And second, now the next part is why do we write it down this way? And this will be solid state physics. It's a good chance to talk about this. So you will see two parts. Now, the high temperature result, this constant result, there's a name for this. So at this part of the curve, this is called Dulong Petit result. So this is Dulong Petit. Okay, Dulong Petit law even. So what does it mean? So here, it basically is a way to argue that when at a very high temperature limit, you will be able to calculate the internal energy of the solid. So this internal energy has two parts. One is the kinetic part. One is the potential, the elastic part. So how do we form a solid? We form a solid by having how do we put all these atoms together? Why do we have a stable form, which we call solid? That is because there is some chemical bond, right? So from the chemistry viewpoint, you say, because all these atoms are connected to each other by bonding, through bonding. So I have a regular array of atoms, and that's because of bonding. But for physicists, we don't we can use bonding, but when we describe this system, we actually will draw something like this. We'll draw one atoms, another atoms, another atoms. We are going to connect them by springs. Okay, so from here, you have some potential energy, which is due to the elastic potential of the spring. Okay, an equipartition theorem tells you if you have a quadratic degree of freedom, for example, a half spring constant x squared, this is called the quadratic degree of freedom. Another quadratic degree of freedom that is familiar is the potential energy, right? That you have some constant. This is spring constant. The mass of the particle is also a constant, and what it varies goes quadratically. Okay, so this is called quadratic degree of freedom, and each quadratic degree of freedom will contribute a half kBT. Now this is Boltzmann constant. This is spring constant. Okay, so at high temperature, you know exactly how to calculate the total internal energy. You sum up all this degree of freedom, and you will find that the internal energy is proportional to kBT. Okay, for the solid, right? We have now that to complete the picture, you need to learn a little bit more about the solid state physics. You have 3n degree of freedom, so don't worry too much about that. But what you should understand is your internal energy will be proportional to kBT. The precise form is actually 3n kBT. Okay, and therefore heat capacity is the temperature derivative. You have 3n times kB, which is temperature independent, and this explains why this is constant here. Okay, at high temperature, that's when you have this simple Dulong Petit law. And I can even do more than that. You see, this is in the unit of per mole. How do you do per mole? You do per mole by looking at 1 mole of particle. Then this will be 3 times n. This n, the number of particle, will be Na, right? So this allows me to to analyze 1 mole of material. And you will see this Na times Kb is the gas constant. Gas constant is 8.3. So if you multiply by 3, that will give you about 25. And actually, you can have very concrete prediction. So this number is not that random. When you keep going and excite all the mode that allows you to store the energy, you have Dulong-Petit law that tells you the heat capacity. The molar heat capacity will approach 3R. Okay, and that the 3R is about 25, and this number is very nicely shown here. Okay, but of course, this is not the full story because Dulong-Petit tells you there's no temperature dependence. But if you go to low temperature, you begin to see things like this, and that requires you to understand what happens. Okay, so this is Dulong-Petit tells you this result, and at low temperature, what happens? At low temperature, the reason you have heat capacity going down is because now if we look at this spring, we should really solve the equation of motion for this problem really carefully, right? That is to say, you have to look at the force due to the spring, and then you have to look at what happens to these atoms. So this will give you something called lattice vibration, and this lattice vibration is the wave picture, right? You get the lattice wave. The atoms will vibrate, will move in a coherent way that you can use a wave theory to describe this motion. Okay, so this is the wave part of the picture. And what is the particle part? The particle part is the phonon. It's what we call the phonon. And this a good preview here for you. Right? Remember this. I'm very confident that towards the end of the lecture, I will have time to talk about the statistics. When I talk about statistical mechanics, I will be able to analyze the statistic for these particles, these phonons. Okay, the origin is coming from this kind of solid state physics, but I will just assume there's one type of particle which we call phonons, and this will obey the Bose-Einstein statistics. And I'm going to give you this TQ law. Okay, so this part is due to phonon. And once you write down the theory carefully, you will see this T cube behavior at low temperature. And moreover, once you do this theory fully, you will also be able to get the Dulong-Petit law. That's to say, if you go to the high temperature limit, you will also get this constant behavior. So rather than using Dulong-Petit as the most fundamental result, eventually we will see that we will be able to solve this problem by carefully analyzing the statistics of this obeyed by these particles. And we will be able to extract the low temperature limit as well as the highest temperature limit, and actually also the intermediate case. The intermediate case is there, but it's just uglier. You cannot express it in such a simple way. Okay, so this is one goal that we aim to achieve. Okay, and now if you are still with me, you will complain. Why is this term here? So this term is due to electrons. Okay, this is due to not all kind of electrons. This is due to the conduction electron in the system. This term is here because you have electrons that move in your solid. That is to say, if your solid is not a metal, that is to say you do not have electrons that can move around, this term will become zero. And this is a chance to tell you why we do low temperature physics. Okay, so listen carefully. This result is valid when your temperature is lower than the characteristic temperature. Okay, even if you are low enough, let's say you already go to sufficiently low temperature to see the T cube term, but this T cube term goes up a lot faster than the T linear term, right? Let's say you start from T equals 0, you raise your temperature. Of course, it depends on the relative size of gamma and beta. Let's pick the typical value and trust me here. And once you raise the temperature, you will see that the T cube term is very quickly dominating the heat capacity. So you have at low temperature, you have two channels. For a typical solid, you have at least two channels to store your heat. Okay, there's heat capacity, right? One is to explore the lattice wave, the phonon part. The other one is to take advantage of the conduction index. Okay, and if you want to see the gamma T term, you need to go down to very low temperature in order to stay in the temperature range where this T cube term is not yet too overwhelming. Okay, and that is the reason why we examine material under extreme condition. Why do we want to measure our metal to very low temperature? First, if I go down to very low temperature, I find the linear term is completely absent. I know I have an insulator. And if I have a metal, these are all metal, you cannot even see them. What you really see is mostly the T cube term. If I have a metal, I can learn a lot about my system by looking at gamma. Okay, so this is the full story. And once I go to high temperature, you have this constant. You might say, there's still this linear T term, but they are there. It's just they are too small. You will not be able to see them. So at high temperature, the heat capacity is mainly dominated by the phonon. Okay, so that is something for you to keep in mind. So the lesson here is you should be able to do some thermodynamics and convince yourself that this absolute value of S can be measured. And second, if you have more knowledge from other courses, you'll be able to provide more understanding, deeper understanding on this kind of problem, right? I just write it down. I didn't really derive it for you, but I write this down and show you what you can expect. Okay, that's all for this chapter. Now the next chapter is on is chapter 5, which we call the analytical thermodynamics. We are going to really do a lot of derivations. Yeah, you have a lot of equations. Okay, so I think this is a good time for break. Let's come back at 12:35, and we are going to start from here. Okay. All right. See you soon. Okay. Welcome back. Okay, so this is chapter 5, analytical thermodynamics. So we are these are the topics we want to cover. I should be able to talk about the first two today, and then the other two on Wednesday. Okay, so let's have a look. Actually, get rid of this. Okay, so you have seen a lot of energy-like quantities. Actually, you have seen several energy-like quantities in thermodynamics, and they are very important. So energy-like quantities. So this is to motivate you. Okay, what we want to achieve today. So what we want to achieve today is to give you more energy-like quantities. So this is energy-like quantities. For now, so we are still talking about a system with a fixed number of particles. This is something we should keep in mind. Okay, so now we already saw. We already met internal energy U, enthalpy H, and then these are energy-like quantities that we picked up when we analyze our system. Okay, so now we are going to talk about PV system. So for this kind of system, we have the thermodynamic coordinate for us. They are important, include pressure, volume, temperature, and entropy. Okay, so that is exactly the quantities we use to build our first law. So our first law and the second law combined tells us we have this result. Okay, so let me highlight this. So this is for a fixed number of particles. Okay, that is to say, for example, when we write this, what is this? This is actually a partial U, partial S at constant V. Okay, and this is one thing we don't write is we don't write this, but you should keep in mind that we keep our N constant, because later we are going to relax this and look at more generalized form. Okay, so this is for a fixed number of particle, we have this. Okay, and now this is also another chance for you to view this a little bit more. Why do we call this the potential function? Because I told you this has this quantity here is a little bit like the force. So if you have the derivative of the potential, this tells you it's a bit like how you define force in mechanics, right? You have once you know the potential profile, you take the derivative, you can read the force. Okay, and naturally we want something else that can give you the same function. So if you look at here, we have these quantities, right? We have the mechanical part. So these are the mechanical part in the first law, mechanical part. And this is the thermal part. And we want to have other thermodynamic functions that can emit other natural variables. Okay, so for U, we already mentioned this. So U, the natural variable of U, when you write it this way, you know the change of U is driven by the change of entropy and the change of volume. So this is how we define, how we write it before. So these are the natural variables, and I spend time to justify to you why this are important. And from here, you can see that if I do not want, for the PV system, if I want other natural variables, you don't really have that many combinations, right? So you can change it one by one. For example, if I do not want volume as my natural variable, the mechanical part, I can replace it by pressure, and that is that is another thermodynamic potential function. Okay, so we call this kind of energy-like quantity, this U, as the thermodynamic potential function. So let me take it step by step. So this is a thermodynamic potential function. And U is naturally one of them. If I know how to replace V by pressure, I will get another one, and you have seen it. This is H, the enthalpy. Okay, and now if you don't like the entropy, and if you want to replace it by temperature, you have another two, right? So if you have T and V and T, as well as T and P, so that will give you two other functions. So those will be given to you very, very soon. So those will be Helmholtz function, F, and Gibbs function, G. Okay. So so for the internal energy, we already know the natural variables are S and B, and H, you also already saw it. There's a parallel between H and U, the internal energy U. So that is you will replace V by P. So S and P are natural variable. Okay, and then F, the Helmholtz function, will be the one with T and V as the natural variable. And then finally, you have the Gibbs. Gibbs is very nice. You have temperature, which you know how to measure. Pressure is also a kind of a good quantity to control. So these are very useful in chemistry. Okay, so you have T and P as the natural variables. It's something you can control and allow you to write this down, and then you do your thermodynamic with G as the starting point. Okay, so now you can see if I have different constraints in my thermodynamic system, I would like to be able to have a different starting point. I don't necessarily want to always start from U. It's just this internal energy is how we develop our thermodynamics. Okay, so if I want other energy-like quantities, these thermodynamic potential functions, I need to learn how to come up with the good expression for them. Okay, so a little bit more to say here. This is rather important. This is also a very annoying situation which I do not have a way to fix, and that is the problem of notation. So if you pick a book which is new, you really have to check, because sometimes this internal energy is called E, energy E. That is not too bad, actually. I can accept this. And then the Helmholtz function sometimes is called A. This comes from a German word which I don't know how to pronounce. Right? So sometimes it takes the notation of A. This is also okay. It's not too much of a problem. But the real problem is this. Gibbs function sometimes is also called F. So you have to be very careful because then you will be very confused. You suddenly see F in many equations, and you don't know why the natural variable is not T and V. Okay, so this is the most dangerous part, actually. So the notation can be confusing in different books, can be different in different books. So this is a fair bit of warning that you need to pay attention. And the other thing, of course, is to check the sign of the first law. This is another thing I mentioned earlier. Okay, so this is one. And the other thing to keep in mind is all these energy-like quantities, you haven't seen the precise form, but all these are function of states. They are all function of states. Okay, so these potential potential functions are all function of states. Okay, so now Maxwell relation is the big thing. We will get there soon. Okay, so now let me define something for you. So I really mean define. So this is not a derivation. So I will define my enthalpy. Define is related to the internal energy like this. Okay, so this is something you saw when we discussed the heat capacity at constant pressure, right? We extract something to make the equation more beautiful, and we say, why don't we define this combination as H, the enthalpy? Okay, and now we did it that way, but now we should look at it differently. What else can we say? we should define our new thermodynamic functions such that I can have this kind of nice property. That is to say, once I define it that way, I will be able to have my enthalpy emit a different natural variables. Okay, so let's see how we achieve that. Okay, so now let's look at the change of H. Let's do the differential. So I will have this. Once I have this definition, you will see very clearly this is du plus pdv plus vdp. And according to my first law, so let me write the first law. First law is TdS minus pdv. This is the first law, and then the rest I just copy. Okay, and once I do it this way, I can have nice combination. I will have TdS. I will have nice cancellation. I have the TdS plus VdP. Okay, so this again is how I should interpret this equation. That is to say, the change of H is driven by the change of S and the change of P, and therefore the natural variable for H, the enthalpy, is S and P, pressure. Okay, so this is this tells you this definition makes sense. It makes sense because it allows me to achieve what I want to achieve. Okay, this is one. And now we can quickly do the other two. I will do it. Helmholtz F. What can I do? So this is 2. How do I define? How do I define F? Okay, again, I don't want you to memorize all this. That's why it's better if you try to understand the derivation. Otherwise, you can very easily make a mistake with a minus sign somewhere. Okay, the minus sign problem will come up soon. Now, F, again, I compare with my U, right? I want to change, I want to keep the mechanical part. So the Helmholtz function, I want to keep the mechanical part. I want the volume as the natural variable. I want to change from S to T. And the hint is identical. I have this TdS here. I want to kill this TdS. How do I do it? I will define it such that when I take the differential, I will be able to kill the TdS, the positive TdS. Okay, so I can then do it like this. I will arrive from the internal energy and I will minus Ts. Okay, because my TdS is positive in du when I write du. So now I want df to have sdt rather. All right, so I would do it very quickly. I do the differential. I will have du minus TdS minus sdt. Okay, and then you will see the TdS term will cancel, and sdt is the thermal part, and the mechanical part will be the same as du, so I will have minus pdv. This is where I think you need to be careful. I see the minus sign appear. Yeah, so that's why if you memorize too much, this is the kind of thing that you can get into trouble. Okay, so here I achieved the goal of F with which emit T and V as the natural variable. So that's this definition again makes sense. Okay, and then the last one is the Gibbs function G. Okay, so now you should already know how to do it. I want a definition that allows me to have this. Okay, so I have two starting points. I can either start from F and replace V by P, or I can start from enthalpy H and replace the thermal part. Okay, and then of course they should be equivalent. In the end, you get the same result. So I would just write it down. I can either start from F and then replace the mechanical part, which means I want to start from F and replace it to VDP. So I need to, this is minus, so I need to add PV. Okay, I think you can get the feeling already right now. Or I can also start from H here, and then replace the TDS part. I want SDT. This is plus, so I need to kill it by adding a minus TS term. Okay, and this will all give you the same result. And for future reference, sometimes people write everything out starting from the internal energy, because internal energy is what we use as the most fundamental way for the development of this course. Right, so I can write U plus PV for H, right, and then minus TS. Okay, and this form will be used when we discuss phase transition. Gibbs is very useful when we discuss phase change, right? So DG, the end result is this. I will just quote the end result. Okay, so this tells me G, the change in G is driven by the change in P and the change in T. This is let me complete that sentence. When we discuss phase transition, this is very useful. In particular, we like to talk about the phase transition, for example, of water, H2O. And we know we can control, say, the boiling point by varying the pressure, right? We take the water to the mountain and we try to boil it, the boiling point will be different. Okay, and there's a phase boundary that depends on the pressure and temperature. And therefore, we can draw some kind of phase diagram on the plane of temperature and pressure. And there, it will be most natural to use a Gibbs function to describe the situation. And that is exactly what we are going to do when we discuss phase transition. Okay, so I define this for you. And now I can give you one more thing. Okay, and that is the Helmholtz function. So there is the Maxwell relation, and I'm going to use the Helmholtz function as an example. Okay, so I'm going to look at this in more detail, and that will give me the Maxwell relation. So I'm going to take the Helmholtz result. What is the result from our derivation? Okay, I remember we want T and V as the natural variable. And I also know with our definition, we managed to get this result, PdV minus SDT. Okay, so this is here, PdV minus SDT, both are negative. Okay, and when you look at this, now you should already know how to write this coefficient here. This coefficient minus P is nothing but the partial derivative of F with respect to volume, keeping temperature constant. Okay, and similarly, minus S, the entropy, is also you can also write it, right? So this is what you know from before. You know how to relate all this coefficient to the first derivative. And why don't you keep going? Why do you stop here? Why do you want to just stop at the first derivative? Okay, the argument is this. This F is a function of states. And therefore, this df is an exact differential. right? F is a function of state. So the differential of F is an exact differential or proper differential. So you should be able to go further. What can you do? You can take the second derivative. More importantly, you take the mixed derivative. So the mixed derivative are equal, right? This is a change of argument which we spend time in week 1. Okay, now let's do it. We already differentiate with respect to t, and next we should differentiate with respect to v. So what I have is I will sorry, we already differentiate with respect to v. Now we want to differentiate with respect to t by keeping v constant. So I will have this result. Right? Okay. And that is, by definition, equivalent to taking the derivative of this can be viewed as that doesn't make sense. This is wrong. Sorry. Okay, so this is partial f partial t with. Okay, so this entropy is a result of first differential of f with respect to t, and now the second differential should be with respect to volume instead. Okay. Okay, let's tidy up this minus sign. We have the Maxwell relation. So this is one of the most important results. So this Maxwell relation tells you have this. Okay, this is the Maxwell relation based on F. And you have 4 thermodynamic potentials, so you can have 3 more Maxwell relations. Okay, so in the note I have all of them. Let me see if I can pull them out quickly. Here. Okay, so this is all Maxwell relations that you can use for solving thermodynamic problems. So that is why I say you will have a lot of new tools in your toolbox. So this is Maxwell relation. Okay, I will tidy this slide later. Okay, you get all these Maxwell relations. Okay, so the one I derive is based on F, right? This one here is this one. Look. Okay, and the rest can be obtained in a very similar manner. Okay, so do you want to memorize this? If you want, you can try. In the textbook, they provide ways for you to remember. For example, you can see some pattern. You can develop your own pattern, or you can look at the textbook. For example, you see when you see t at the numerator on the left-hand side, on the right-hand side you have s. Okay, so this conjugate variables are if you look at this equation, it looks like they are on the diagonal, right? When you have pressure here, you have volume here. And then here as well, you have P times V, you have PV like this, TS like this. So those are different ways to memorize them. And sometimes you have a minus sign. When do you have minus sign? You have minus sign when T and V on the same side. Okay, you have T and V here, and you have T and V here, then you get a minus sign. So those are the ways to memorize. But I still recommend you to learn how to derive. That is better, I think. And then another message you should get from here is this Maxwell relations tells you something quite profound. For example, look at the one I derived. Look at the one I derived, this one. On the right-hand side, you have something like this, the rate of change of entropy when you change the volume. This is a very difficult differential to even imagine. Right? I change the volume, the entropy of my thermodynamic system changes. This is a very, very difficult concept to visualize to begin with, not to mention measuring it. Okay, but Maxwell relation tells you how to proceed. This is an identity. It tells you if you know how to measure this quantity, you will be able to relate this to the change of the entropy. Okay, and in my opinion, this is really something you should take home. So Maxwell relation has this value. It allows you to relate something which is harder to measure to something that you can readily measure. Particularly anything when it involves entropy, it will be difficult. Okay, so that is entropy. Out of 4 variables, entropy always shows up on one side, and the other side will be something that is easier to imagine, and that is more readily measured in the lab. Okay. All right. Right now, I wrote down all this definition. I gave you the goal. I told you what I want to achieve. I told you I want to achieve this kind of situation when I have different natural variables. That is to say, when I have different constraints placed on my system, I want to have different starting point, and those will be my newly introduced thermodynamic